Chemistry of solution of a solid element. In the solvent rectangular delicacy is called the standard heat of formation of the solution. If a solution contain n moles of solvent per mole of solid, then delta HF solution is equal to delta HF solute plus delta HSN. The standard heat of reaction involving solution may be calculated from heat of formation of the solution. For example, for the reaction 2HNO3, solution equals R equal to 25. R is based on table B11. CaOH2 equals R equal to infinity, meaning dilute CaOH2. Mix both equal to CaNO3 2 equals dilute plus 2H2O liquid. The standard heat of reaction is delta HR equal to 1 mole CaNO3 to delta HF CaNO3 2 equals plus 2 mole of H2O minus 2 mole of HNO3 minus 1 mole of CaOH2. Delta HF CaNO3 is from table B1. Delta HF is table B1. This is table B11. Table B11. So the delta HR for this section is 114.2 kilojoule. Example 1, calculate delta HR for the reaction H3PO4 equals dilute plus 3 NaOH equals R equal to 50. Example 1, 3PO4 equals R dilute plus 3 NaOH sodium hydroxide R equal to 50. So R is equal to mole H2O per mole solute. In this case, it's sodium hydroxide equal to Na3PO4 equals dilute plus 3H2O liquid form. H3PO4 equals is delta HF at the heat of formation is equal to negative 309.3 kilocalorie per mole equal to negative 1,294 kilojoule per mole, which is from Perry Chemical Engineer Handbook. There's no data for H3PO4 in table B1 or reference books 1. For NaOH equals R equal to 50, so delta HF NaOH, this is a solution, is equal to delta HF NaOH solid plus delta HS are equal to 50. So delta HF, the first term here is from table B1, while the delta HS is from table B11. This is heat of solution equal to negative 426 minus 42.51. So delta heat of formation, delta heat of delta HF. Delta HF solution for NaOH is negative 469 kilojoule per mole. For an A3VO4, the delta HF is negative 471, also from Perry Chemical Engineer Handbook. In kilocalorie per mole, mm, convert to kilojoule per mole is negative 1900. For for H2O liquid, delta HF is from table V1. So delta HR is equal to product minus reactant, so negative 130.1 kilojoule. Example 2, if 5 mole of NaOH dissolved in 250 mole of water in is neutralized completely at 25 degrees C with dilute phosphoric acid, what is the intended enthalpy change? For this case, we have from example 1 the delta heat of friction. So 3 mole NaOH is from chemical reaction, 5 mole NaOH is from the separation. So divide by 3 mole and multiply by 5 mole NaOH, you get negative 217 kilojoule. Is produced to neutralize NaOH, 5 mole NaOH. Exercise. The heat of formation of delta is delta HF equal to negative 100 kilojoule per mole. Heat of solution of A in solvent B delta HS are equal to 50 mole B per mole A equal to negative 10 kilojoule per mole, and delta HS R is dilute equal to negative 15 kilojoule per mole. What is the standard heat of formation of A solution or equals R equal to 50 relative to B and the element of A? For answer the first question, it is negative. Refer back to the equation delta HF solution equal to delta HF formation plus delta HS heat of solution. So in this case, negative 100 kilojoule per mole minus negative 10 kilojoule per mole, delta HF and delta HF. So the standard heat of fusion of E is equal to negative 110 kilojoule per mole. What is delta HF for E solution R dilute relative to the same references? So for dilute, still using the similar equation, delta HF solution equal to delta HF plus delta HS. So in this case for dilute, solution is negative 100 kilojoule per mole plus negative 15 kilojoule per mole equal to negative 115 kilojoule per mole. What is the enthalpy kilojoule per mole A of a solution of A in B at 24 degrees C for which R equal to 50 relative to B and the element of A at 25 degrees C? So enthalpy of solution A in B is equal to negative 100 kilojoule per mole A. 2b. What is the enthalpy of a solution containing 5 mole of A in 250 mole of B at 25 degrees C relative to A, S, and B, L at 25 degrees C? What is it relative to B, liquid, and the element of A at 25 degrees? So H 25 degrees C is equal to negative 110 kilojoule per mole A times 5 mole of A. So the answer is negative 550 kilojoule. Fuel and combustion. The use of heat generated by a combustion relation to produce steam which drive turbine to produce electricity may be the single most important commercial application of chemical reaction. The analysis of fuel and combustion reaction have always been an important activity for chemical engineers. Fuel burned in power plant can be in the form of solid, liquid, or gaseous. So solid fuel is principally coal or coke. Liquid fuel is, oh, another one is, for solid fuel is wood and solid garbage. For these two, it fall under gasification. For liquid fuel is principally hydrocarbon obtained by distilling crude oil. Gaseous fuel is a natural gas, such as methane or propane. Coal contains primarily carbon and combustible hydrocarbon, but also has substantial amount of non-combustible ash and as much as 5% sulfur by weight. This minor constituent often raise issues in the use of coal and stimulate the following. To stimulate the following question. What become of the sulfur when coal is burned, and what about the ash? Suggest two possibility of for the ash. In view of the answer to the preceding question, why might coal be less desirable as a fuel than natural gas? What might prompt a power company to use coal as its primary fuel despite its drawbacks relative to liquid or gaseous fuel? The heating value of a combustible material is the negative of the standard heat of combustion. The higher heating value or total heating value or gross heating value is the delta H combustion with H2 liquid, H2O is the combustion product, and the lower heating value or net heating value is the value based on H2O vapor its product. Since delta Hc is always negative, the heating value is positive. To calculate a lower heating value of from fuel from a higher heating value of 5 you must determine the mole of water produced when 1 mole of the fuel is burned. If this quantity is designated N, then HHV, high heating value equal to LHV plus N delta HV H2O at 25 degrees C. The heat of evaporation of water at 25 degrees C is delta HV H2O at 25 degrees C equal to 44.013 kJ per mole. If a fuel contains a mixture of combustible substances, its heating value or lower or higher is HV equal to XI HVI, where HVI is the heating value of the high combustible substance. If the heating value are compressed in units of energy mass, then Xi is the mass fraction. If the heating value is energy per mole, then Xi is the mole fraction. For example, a natural gas contains 95% methane, 15% ethane by volume. The heat of formation of methane, methane at 35 degrees C and 1 atm with water vapor as the extreme product are given below. CH4 gas plus 2 oxygen equal to CO2 plus 2 H2O vapor. Solid H3 is contained negative 802 kilojoule per mole. The second reaction is C2H6 gas plus 7 over to 3.5 oxygen gas form equal to 2 CO2 vapor plus 3 H2O vapor. Calculate the higher heating value kilojoule per gram of the natural gas. Since the heating value per unit mass of the fuel is desired, we will first calculate the composition on a mass basis. So 1 mole fuel, the basis is equal to 0.85 mole CH4 methane and 0.15 mole ethane C2H6. So from here you can calculate, you can get 13.6 gram of CH4 and 4.5 grams C2H6. Total is 18.1 gram total. So the mole fraction, the mass fraction is 13.6 gram over 18.1, which is 0.71 gram CH4 per gram of fuel. And for ethane, it's 0.29. The higher heating value of the component are calculated from the given heat of combustion, which are the derivative of the lower heating value as follows. HVCH4 equal to LHV, lower heating value, plus NH2O, delta HV. So LHV is here, equal to heat of combustion. Although the heat of combustion is negative, LHV is positive, plus 2 mole H2O per mole of CH4. 44.013 delta HV of H2O. You can check it in table B1. And 1 mole over 16 gram of CH4. So the higher heating value of methane is 55.6 kilojoule per joule. For higher heating value of C2H6, which is 1428 kilojoule per mole, C2H6 is from delta HC, heat of combustion, plus 3 mole H2O per mole of C2H6 per mole of ethane. Is a delta HV H2O, so 1 mole have 3 gram of C2 ethane. This is a more molecular weight. So equal to 50 kilojoule per gram. The higher heating value of the mixture is from the question 9.6-3. So our case, this is a mass fraction times higher heating value for ethane and methane. The HHV mixture is 54.7 kilojoule per gram. Higher heating value of several common solid, liquid, and gaseous fuel are given in section 24 of Perry, Chemical, and Linear Handbook. Such value often depend upon the source and type of particular fuel, hardwood versus softwood, subbituminous versus bituminous coal, and given value should only be used as estimate. Additional estimate of heating value for a variety of solid, liquid, and gaseous fuel can be found in the biomass energy data book 10. The standard heat of reaction C4H10 For butane plus oxygen is equal to carbon dioxide and water is 2658 kilojoule per mole. What is the lower heating value of N-butane and the higher heating value? The lower heating value is 2658 kilojoule per mole. The higher heating value is HHV equal to LHV plus plus mole N delta HV for water. In this case, 5 mole of water times 44.013 kilojoule per mole, which is delta HV H2O at 25 degrees. The answer for higher heating value is 2878 kilojoule per mole. Exercise 2, the gas mixture contains 40 weight% H2 HHV equal to 143 kilojoule per gram and 60 weight% CH4 HHV 55 kilojoule per gram. So here I'm using a mass fraction. Calculate the higher heating value of this mixture in kilojoule per gram. So HHV for exercise 2 we use equation equation 9.6-3 HHV equal to N HHV plus N is HV equal to XI HV. So X is mole or mass fraction. Mole fraction or mass fraction. So let's guess 0.4 times 143 plus 0.6 times 55. SHV is equal to 90.2 kilojoule per gram. Fuel and combustion adiabatic flame temperature. When a fuel is burned, a considerable amount of energy is released. Some of this energy is transferred out of the reactor as heat and the remainder raises the temperature of the reaction product. The less heat transferred, the higher the product temperature. The highest achievable temperature is reached if the reactor is adiabatic and all of the energy released by combustion goes to raise the temperature of the combustion product. This temperature is called the adiabatic flame temperature, T adiabatic, TAD. Calculation of adiabatic flame temperature follow the general procedure outlined in section 9.5b previously. Unknown stream flow rate identified beginning by natural balance reference condition are chosen. We can calculate the frequency are calculated in specific enthalpy of product that are expressed in terms of product temperature. Only data H for the process is evaluated and substituted into energy balance with data H equal to 0 or derivative. So data H equal to 1 mole of heat times data H C combustion plus H N I H I for outlet minus for product minus reactant. As the reactant is adiabatic, V equal to 0 if shaft and kinetic engine energy negligible compared to each term in above explicit for data H, then can simplify this equation to 9.6-4. In equation 9.6, explore the value of I are the mole of oxygen, nitrogen, if oxygen is part of a heat stream. Here, 2 and H2O associated with the complete combustion of 1 mole of fuel. T naught is the temperature of each species, and the reference condition for the calculation of those used to determine the value of delta H C. If the third order polynomial heat capacity formula in the table below to be used to determine are used to determine delta Hi for each product species, the equation and basic dashboard become a fourth order polynomial equation. Example for adiabatic flame temperature, liquid methanol is distributed with 100% excess. The engineer is aiming the furnace must calculate the highest temperature product. Furnace able to withstand so that the appropriate material of construction can be chosen. From this, perform this calculation assuming that methanol is fed at 25 degrees C and the air enter at 100 degrees. So highest temperature means T adiabatic. Assuming the process is adiabatic, one basis is 1 mole CH3OH per assume complete combustion from table B1 CH3OH plus T20 oxygen equal to carbon dioxide plus water, delta HCC is negative 226 and 6 kilojoule per mole. 1 mole, so you have 5 unknown. Calculate component amount, so NO2 theoretical is 1.5 mole. And N1 equal to 1.5 mole equal to 3 mole oxygen fat. And 3.75 mole and 2 per mole of oxygen and 3 mole oxygen equal to 11.28 mole into fat, nitrogen fat here. N1 mole and 3.76 N1 mole nitrogen. Material balance yield N2 equal to 1 mole CO2 and 3 equal to 2 mole H2O and 4 equal to 1.5 mole oxygen and 5 equal to 11.28 mole nitrogen. So to solve this equation, there's no other way. Need to use Excel and the temperature T8 is 1127 degrees C. Thank you. So what we have learned in this topic, heat of formation, the concept of heat of friction, exothermic and endothermic friction, heat of formation, combustion, heat of combustion, standard heat of formation, combustion and reaction, heating value of a fuel and adiabatic flame temperature. Determine the heat of reaction from heat of other reaction using Hess law. Determine standard enthalpy and internal energy of reaction from non-standard heat of formation and heat of combustion. Write and solve an energy balance on a chemical reactor using either the heat of reaction method, taking internal product species as a from the enthalpy solution, or the heat of formation method, taking the method species as reference and specify which method is available for a given process. Write the process path implicitly adapted when each method is used. Solve reactive system energy balance problem. For A, the heat transfer required for specified inlet and outlet condition. The outlet temperature corresponding to a specified heat input and replicate. In C, the product composition corresponding to a specified heat input and a specified outlet temperature. Convert the higher heating value of a fuel to a lower heating value and vice versa. This is the reaction to prepare this slide. So, thank you.